Welcome to A2 Hardware. At AS level, you looked at the basic von Neumann architecture, where a single processor fetches and executes instructions sequentially. But modern computing demands immense speed and scale. This unit is about how engineers push physical hardware to its absolute limits, and when hardware is not enough, how we use software to emulate it entirely. You will need to evaluate these architectures for Paper 3, moving past basic definitions to justify complex engineering choices. We start by examining processor performance. You will evaluate how clock speed, cache size, bus width, word length, and the number of cores interact to dictate overall throughput. Then we dive into instruction pipelining. Instead of waiting for one instruction to finish before starting the next, modern processors overlap the fetch, decode, and execute stages. You will trace machine code instructions through the pipeline, calculate exact cycle improvements, and learn how architectures resolve the data and control hazards that threaten to stall the system. Next, you will compare the two major design philosophies, reduced instruction set computing and complex instruction set computing. You will evaluate their trade-offs in memory usage, compiler complexity, instruction formats, and how they handle interrupts. Paper 3 requires you to move beyond simple definitions and justify which architecture is best suited for a specific commercial scenario, balancing hardware simplicity against software efficiency.
When a single core reaches its physical limits, we multiply them. You will classify architectures using Flynn's taxonomy, distinguishing between single instruction multiple data and multiple instruction multiple data systems. We will map exactly which hardware resources are shared between cores and which remain private. Crucially, you will explain the software challenges of multi-core processing, like race conditions and deadlocks, and explain why upgrading hardware does not automatically make every program run faster.
Finally, we explore virtual machines. A virtual machine is a software implementation of a physical computer system. You will see how a hypervisor sits above the host hardware, allocating resources to create isolated, independent virtual systems that run their own operating systems. You will evaluate the commercial applications of this abstraction, from server consolidation and cloud computing to testing legacy software, while balancing these immense benefits against the inevitable performance overhead.
By the end of this unit, you will be equipped to evaluate the hardware and software strategies that drive high-performance computing. You will calculate pipeline efficiency, justify architectural choices between RISC and CISC, analyze multi-core systems, and explain the enterprise value of virtualization. These are the high-tariff concepts that separate top candidates in the advanced theory exam. Take your time, master the terminology, and get ready to apply it.